While discussing virtual memory and paging, there are other criteria that need to be discussed for further improvement in the system. One of these considerations is prepaging. Remember that when a process is started, it has no pages in memory. So the first instruction to be executed will cause some page fault. Typically, the page that contains main will be brought. And the first instruction typically would be touching local variables as well as global variables. So another page fault will occur because of the global variables, and it will go this way. Now, also when you try to access a file, typically, especially for the text files, you start from the beginning of the file and access it in a sequential manner. So it is possible actually to make some estimations of the following page faults that might occur, and the system, if you can properly predict it, the system can page in those pages that are in the swap space into the memory directly, so that when you need to access, you won't have a page fault because it's already in memory. So those pages will be brought while the swap disk is actually idle. So this will significantly improve system performance and response time. But of course, this heavily depends on how good you can make that estimation. It is possible that you estimate that, let's say, page 10 will be required. So you pre-page page 10, but actually the process maybe is not going to access page 10 for a long time. So that would be an incorrect guess. So the system's performance heavily depends on how good you can make that estimation. So assume that your pre-paging, let's say, S pages, and unfortunately your estimation is not 100% true. So let's assume that alpha % of the pages you have pre-paged are actually being used. That means 1 minus alpha was the wrong estimate. So now whether pre-paging is a good idea or not depends on how much or how many page faults we are saving from, which is defined by S times the alpha, and the cost of incorrect estimations, incorrectly pre-paged pages which were actually never accessed. You just bring them and that was a bad estimation, and this would be S times, this time 1 minus alpha. So depends on this ratio. If alpha is very low, then pre-paging definitely is not a good idea. You don't apply it. But if not, it might be good. Another thing you need to consider is the page size. What should be the page size? Now, first of all, if you're for example designing an operating system for an existing CPU design, there is not much you can do. The CPU design itself imposes some page size, so you have to design your operating system according to that CPU. However, if, for example, you're working in a company which is also designing the CPU, or at least collaborating with such a design, then you might have a say in the page size. So the page size should be determined by considering many things like fragmentation. If the pages are small, since if there's no bias, half of the last page is fragmented, internal fragmentation. If the page is small, you will have less fragmentation. If the page size is huge, then 50% of that will still be a lot of memory being wasted. So you will have too much internal fragmentation there. So fragmentation is one thing to be considered. So in other words, from the point of view of fragmentation, we would prefer smaller pages because we want to reduce fragmentation. However, when you have small pages for the same process, if you have small pages, you will have many pages. If you have larger pages, of course, the number of pages would be smaller. Now, if you have small pages, therefore many pages, the page table itself will be too large. And remember, the page table for us is some overhead. So if the page size is small, then the overhead is increasing. So the page table size also prefers smaller. The page table size implies we would prefer larger pages so that we have smaller page tables. We want smaller page tables, don't forget that. Another one is resolution. Resolution in the sense that if you have very large pages, the whole process will be covered by one or a couple of pages. So remember that locality principle? If you have huge pages, you're not able to follow the locality. Okay, so in terms of resolution, if you have smaller pages, your resolution will be higher, so you can capture the localities much better if you have smaller pages. How about the overhead of reading and writing the pages between the memory and the swap device? If your swap device is not SSD, but it's a regular hard disk which contains physical parts that are moving, because remember, in the case of a hard disk, you're rotating the platters and you're also moving the read-write heads. Now, the movement of the read-write heads and the rotation of the platters, all these are physical operations and they take most of the access time. So the access time is the time you need to retrieve the data from the disk, but it contains rotating the platter so that the data to be read comes under the read-write heads, angular-wise. The read-write head should be on the correct track, or if you're talking about multiple read-write heads, then on the correct cylinder it would be the same thing. And finally, the transfer of this data from the disk into the memory. So that transfer part is the one that depends on the page size. However, the dominating factor among these three time components, the dominating factor is the rotation of the platter and the movement of the read-write heads, rather than the electronic transfer of the data from the disk to the memory. So, in other words, the page size does not affect the I/O overhead significantly. So, from the point of view of the I/O overhead, the page size is not a concern. The number of page faults is of course dependent on the page size. If you have larger pages, then you will find anything you're searching for in those pages. Like if the page is humongous, then the whole process could be fitting into one page. But of course, this has also other drawbacks. The other process will not have enough memory. Locality we already discussed while discussing the resolution, and the the TLB size and the effectiveness of the TLB will also depend on the page size. You will have fewer pages in TLB if you have larger pages. Don't forget that the pages are always in powers of 2. In the very early systems, the page sizes were around 512 bytes. Later, soon, the pages started becoming 4 kilobytes. Today, you will see pages that are 4 megabytes. But so there is no single answer as whether small pages or large pages are better, because they both have pros and cons. But what we can say is, with the advancement of the technology and memory and disks becoming cheaper, the trend is going to growing or larger page sizes. The other thing you need to consider is the TLB reach. TLB reach actually implies how much of the memory is accessible through TLB. Remember, the TLB, translation look aside buffer, was being used to find the pages in a faster manner. But since TLB itself is a cache, it is possible that you have TLB miss. That means what you're searching for is not in TLB. In that case, you have to go to the page table, which was a slow process. Now, therefore, we want that TLB cache to be more effective. That means it should be covering more of the system memory. So that ratio of memory that is accessible, reachable through TLB is what we call the TLB reach. And the TLB reach is definitely dependent on the size of TLB. That means the number of rows in TLB. The larger the TLB, of course, you will have more rows, so the reach will be larger. But another factor is the page size. If you have larger pages, then the TLB corresponds to a large portion of the memory. Ideally, the working set of each process is stored in TLB. We would prefer to see, like, if process P1 is currently in memory and if it's trying to access different memory locations, if whatever it's searching for, it can almost all of the time find in TLB, that's great. If you don't, if the process in process P1 frequently cannot find what it's searching for in TLB, then that means it's experiencing a lot of TLB misses. Therefore, there will be many page faults. So if you increase the page size, it will lead to an increase in fragmentation in the last page, as not all applications require those such large page sizes. There are today systems in which there are pages of different sizes. So you can see them on desktop systems as well as in mobile systems. So having multiple pages allows the applications that require larger page sizes to have the opportunity of using such pages, whereas the others could be living with smaller pages without incurring the penalty of fragmentation. The other issue you need to pay attention to is actually in programming. Now, up to now, we always said demand paging, and in general paging and virtual memory, should be invisible to the application program and therefore the programmers. That means the programmer cannot know what the page size is, should not deal with that. The operating system should be taking care of everything. However, actually, you should be careful while programming. Here we have a very simple but a very representative example that explains how you can do things good or bad. Actually, this is why I always say there is a difference between a computer programmer and a computer engineer. A computer engineer knows the hardware, knows the operating system, and also knows programming. If you ignore how the hardware works and how the operating system works, you can easily fall into the trap shown in the slide. Like, let's assume we have an array that is 128 by 128. Of course, this notation here is not in C language. This is just a pseudo language for you at the moment. But the data is 128 by 128 array, let's say. Now, you have two possible implementations for initializing this array by just zeros. Actually, it's not important whether you're initializing by 0 or 10. That's not the point. The point is accessing this data. If you're trying to access the items, the elements of this array, one by one in a nested loop, where the outer loop iterates for the column and the inner loop iterates for the row, there is a problem here. The point is, see that in the first iteration of the outer loop, you're keeping j constant and you're changing the row number. That means you're initializing the array column by column, whereas in the second implementation, you're initializing it as row by row. Okay? Now remember that arrays are typically stored row by row. So if, for example, your pages are, for a better representation of this problem here, let's assume that your page size is equal to the size of 128 integers, whatever the integer size is. Assume that each page can store 128 integers. Then that means in each page you're storing actually one row, since the arrays are stored row by row. So one row will be filling one full page. So each row will be in a separate page. So in the second implementation, since you're fixing the row first and then just changing the column, that means you have a page fault for the first page, okay, where I is 0. So let's call that page 0 or row 0. Okay, row 0 is in one page. You bring that page, and then within that page you access each element one by one. But the following 127 accesses do not cause any page faults because it's in the same page. But you had one page fault for the whole row, and you have to repeat it for every row. So the number of page faults will be equal to the number of rows, which is 128. However, in the first implementation, although they look very similar, you take the first column and then visit that column, each row of the column. So that means you have a page fault for row 0. You modify only one element in it, and then you have a page fault for row 1, another page fault for row 2, row 3, row 4. How many times? In the first column, 128 times. In the second column, the same thing repeated. So in total, you have 128 by 128. That means 16,000 page faults, which would be 128 times the number of page faults in the second implementation. So that means while programming, you should pay attention to such things. You should pay attention to how data is stored. This issue, the I/O interlock, is something we slightly discussed actually in the beginning. It is possible that, for example, when you're trying to read from the disk, if you're reading directly into the user space, you typically say read, for example, starting from this position, this much of data. So it will start reading from here, okay, and start filling in this place. Now, what if the operating system now decides to, let's say, the operating system needs a frame for some other process, since your process is already blocked for I/O operation, so it's in waiting state. It might pick this frame here as the victim and page it out. Now, this page does not, this frame does not belong to you anymore. Your page is now written onto the swap, but the disk drive and the disk controller here and the DMA do not know that this frame does not belong to that process anymore. It will keep on writing here because the DMA or the disk controller is not aware of demand paging. So it doesn't know that there has been a page out operation there, and it would be overwriting something else. So to prevent this, what happens is you should be actually locking this frame, the page that's in that frame. When you lock a page, that means the operating system should not be paging that page out. Actually, you should lock both of these pages. Now, it is good, so this pinning of the pages here, locking the pages, is good to, because it prevents this error. But what if there are many such pages that are pinned or locked? In that case, you would be wasting, this is not called wasting actually, you're still using it, but you will not have sufficiently many free pages. So that would constitute one problem. Another one is if somehow, due to a bug or some failure, if these frames remain locked, the operating system somehow loses track of these frames being locked. No one will be able to use these frames later. So you need mechanisms for dealing with such locks. Otherwise, you will experience significant problems. So this will complete chapters 8 and 9. Please read these sections in more detail. These section numbers are given according to edition 8 of the Operating System Concepts textbook by Silberschatz, Galvin, and Gang. For the other editions, you can just find those sections from the table of contents easily.